Hey guys, so today we're going to be talking about empirical and molecular formulae of hydrocarbons. Now, this is a concept you can find in topic one, which it's definitely going to appear in any stoichiometry end of unit test, and it's probably going to appear in your final exams or any overall chemistry exams that you have. And it's if you perfect this topic, it's a pretty easy concept once you get it down. And if you perfect it, then it's a really easy way, good way to guarantee 5, 6, maybe even 7 marks out of your exam. So to start off, we're gonna first define some key concepts. Now, a hydrocarbon is just simply any compound that only contains carbon and hydrogen. Empirical formula, which is probably the main one, is a formula that gives the simplest whole number ratio of atoms in a compound. Now, this may seem a bit complicated to begin with. However, it's just simply a compound in which the ratio of atoms, so in this case, C and H, the ratio between them, so right now it's 1 and 2. And that's the simplest it can get. You can't break it down any further, otherwise, it would go into decimals. So an empirical formula just gives a compound which has the simplest ratio, so you can't break it down any further. And here are some examples, as we said before, CH2, and then hydroxide, carbon dioxide, and H2O. Now, molecular formula, which you see in your everyday, like if you where you see everywhere in chemistry class, is just a formula that contains the actual number of atoms in a compound. Now, this is just the regular molecular formula that you have for different compounds. Like, for example, water, is H2O. Now, while this is also the simplest ratio, you get other compounds, like, for example, here at the end, C6H6, which is also known as benzene. And this is a molecular formula of benzene. Some other examples are carbon dioxide and C2H6. Um, Now here, you might have already done this in class, but there's a conversion from molecular to empirical formula. Now, as we said before, benzene, the molecular formula is C6H6. Now, if you look at the ratio between the carbon and the hydrogen atoms, it's a 1-to-1. It's a 6-to-6 ratio. Now, this can be simplified further by dividing it by 6 on both sides and getting a 1-to-1 ratio. And that'll give us the empirical formula because, as we know before, it gives the simplest whole number ratio of atoms in a compound. So dividing both sides by 6 will give us CH with a 1-to-1 ratio. And a 1-to-1 is the simplest whole number ratio you can get. Here's some other examples. You can get C5H12, and you divide it by 1 because you can't divide C5H12. There's no common divider between 5 and 12. Then some other examples are H2O2. You can divide it by 2 on both sides to get HO, and then C5H10 to get CH2. Now, some uses of empirical formulae in the real world is that mainly they're used to determine the molecular formula of a compound. And molecular formula is probably the most important thing you'd want to know about a specific substance or a specific compound because it lets you understand the properties of the substance and how to react with other compounds. Now, one form of question they might give you to find the empirical formula is they'll say there's an unknown hydrocarbon, CXHY, or at least you write it down as CXHY, where X and Y are just any random integer. And they might tell you that out of the whole compound, carbon contains 80% of its mass and hydrogen contains 20% of its mass. Now, you might realize that you don't have any mass to work with. So how are you going to find the empirical formula? Well, a useful and handy trick that you can use is you can say that, okay, the percentage to go from percentage to mass, you assume that the whole compound, the total mass is 100, because that way you can say that, oh, since carbon contains 80% of its mass, then it would contain 80% of 100, which is just 80 grams. And then you say that hydrogen contains 20 grams. Now, from the mass, we can get the amount of moles by just dividing by the molar mass. So here in this case, we see that carbon contains 80 grams and hydrogen contains 20 grams. And if we divide by the molar mass of carbon, which is 12.01, we can get the amount of moles, which is 6.66. And similarly here, we divide by 1.01, the molar mass of hydrogen, to get 19.8 moles. And then from the moles, if we have the moles of both atoms in the compound, we can divide by the smallest number of moles to actually simplify the ratio even further. So here, if we form a ratio between the amount of moles of carbon and the amount of moles of hydrogen, and we simplify it further, we get a ratio of approximately 1 to 3. Now, when you're doing empirical formulae, you're going to get a lot of decimals, and it might get really hard to determine whether you should round up, round down, multiply, divide, and whatsoever. But in this case, since it's 2.97, it's very, very close to 3. So you just estimate it as 3. And so you find that the ratio between carbon and hydrogen is a 1 to 3 ratio. And so the empirical formula is CH3. Now, here, as I said before, it might be hard to determine whether you need to multiply or just round this up to a 3. So here's kind of like a key for when to do things. If your ratio ends with 0.5, so let's say it's 1 to 1.5. Yeah, it's very inaccurate to just round up because 0.5 moles is a lot relative to 1.5. So you need to multiply the whole thing by 2. So then you get a 2 to 3 ratio. If you get 0.25, you need to multiply by 4. And if you get 0.33, a ratio ending in 0.33, you multiply by 3. And 0.66, you multiply by 3. You don't have to memorize this. This is just try and understand this because these multiplying factors, you're just doing this to make sure that it ends up as a whole number integer. You just want it to end up as an integer because the way we work with ratios is that we don't keep them as decimals. We keep them as whole numbers. So in order to make it a whole number, if it's, for example, 1 to 1.25, is we multiply both the 1 and the 1.25 by 4. So it still remains the same ratio, and it just becomes 4 to 5. However, we get integers. And this is just a short step-by-step guide for how to solve this type of problem. Now, when you're trying to find the molecular formula from the empirical formula, this is the second step to a problem. So we know that the molecular formula is just a multiple of the empirical formula. As we said here for before with benzene, C6H6, we said that if you multiply CH by 6, you get C6H6. And similarly, if you go the other way around. So the way to find the molecular formula from the empirical formula is that we need to multiply the ratio in the empirical formula by a specific integer that we call x. Now, this multiplying factor x, it can be determined by using this formula. X is equal to the molar mass of the compound, the hydrocarbon, divided by the empirical